what does that mean in modern times? How are we utilizing these things to kind of train robotic systems? Now, I'm going to show you a bunch of images, and I want you all to look at these images and think about which of these are real images and which of these are computer generated. It's a trick question, they're all computer generated, but they look very realistic nowadays. It's very different from how it used to be, where I'd have to go out and physically take pictures of dogs for hours and hours and hours on end to train some computer system to figure out what a dog is. But now I can create an abstract representation of a dog, similar to what Katie was saying about these word embeddings. We're sort of creating dog embeddings, cat embeddings, burger embeddings. And this enables more sophisticated robotic systems. So what people were doing before is we had, Google Drive, Google Car, right? We're all pretty familiar with this idea, where there's a driver figuring out how to drive the car, they're collecting the data, and then they train an autonomous car on the data. That's hours and hours and hours of driving. Or perhaps the Google experiment where they bought tens of arms and they constantly had them picking up objects in bins to eventually figure out how to manipulate objects correctly to some intended goal or purpose. And this feels a lot like the Shakespearean problem of putting a bunch of monkeys in front of typewriters, right? It'll eventually work, but it's slow and cumbersome and really the wrong way of thinking about it in my mind. And those two projects, by the way, were done this way just 2 years ago. We've advanced significantly in the past 2 years to where we can create accurate simulations of robotic agents operating in environments that look photorealistic. On the top left here, you'll see these photorealistic images, RGB images, that are being produced by a simulator that look just as good as if I were running a real agent through an environment. This means that I can have clusters of computers running these things to understand an environment, to have a robotic agent learn faster than if I had done this using real robots, which are very expensive and oftentimes, as we find out in the robotics lab, break themselves. So I have put a robot that we have in the lab, the fetch robot, and what I have it doing here is I have it automatically navigating an environment and collecting a data set, which I can then use to automatically segment images to understand its environment, to produce these images as if it were in the real world. And then I can take all of this data and translate it directly onto the real robot, thus saving me hours and hours of time that I would spend manually moving a robot around, manually annotating data. This is a huge step in the field of robotics. Now, some problems I like to try to solve is I've previously done work on controlling a robotic agent for spinal cord patients. And what we were doing is we were taking images, partial images of these objects that were placed in front of the robotic hand, and the spinal cord injury patient was able to use what's called an SEMG, or a muscle activation sensor, to select which object that they wanted to pick up and manipulate, and how they wanted to pick up and manipulate it. But the vision system we were using was very primitive. So something that I've worked on since, it's called shape completion. What we're doing is we're taking a partial image of an object, we're collecting some tactile information from the object that the vision system can't see, and we're creating a geometric completion of the object. The data set that I used to train the system was trained completely within simulation. And this is something that we haven't had the computation power to do until recent times. And this ability allows us to manipulate objects in ways that we couldn't have even fathomed doing before, just purely because we can abstract our systems out so much more than we could before. And so here I'm just demonstrating how I collect the tactile information, how I collect the depth information, this partial image that we create, and what I do to sort of process it. I turn into this voxel grid, I create this nice looking mesh, which I agree, it doesn't look like a Rubbermaid container. It's very rough, it's very crude, but the volume is correct. The depth of the information is correct. And given that we only see what's in red, and we only see what's in blue after touching it, this is a huge step in where we're going. Now, you all can go to this website, view the completions that I've made for you today, and see what we're doing to sort of advance the shape completion idea. Another thing I wanted to mention is Microsoft has been doing some work in this field too, and they've made something called AirSim. And what AirSim does is it's a drone that moves through a photorealistic neighborhood and takes pictures that look just as good as if you were running a real drone through a neighborhood. This is a huge step because now we can create autonomous agents that have segmented point clouds that can learn how to fly around neighborhoods. NVIDIA has recently released an autonomous driving simulator that gives you, again, photorealistic images that a self-driving car would see. And just real quick, I wanted to show you real time what the shape completion output looks like on an arbitrary environment. That's my time. Thank you very much.